So now we move on to Module 6.2, and we'll take a look at a sample problem solution for this section of our module. So in this example here, example number 3, we're given a lot of information within the wording of the problem. So we're told that our mass, m, is equal to 100 kilograms. Our stiffness, k, is equal to 40 kilonewtons per meter. Our damping factor is given to us as our zeta is equal to 0.1. Our harmonic force is given to us as P naught is equal to 500 newtons. And our frequency, our omega, is given to us as 15 radians per second. Our f of 2, we're given this function here that f of t is equal to 500 times the sine of 15t. Our u naught, our initial position here, is given to us as 6 centimeters. And our initial velocity, v naught, is given to us as 0. Now, there's a couple things that we're asked to solve for within this problem. They want us to find the amplitude of the steady state displacement, the phase relative to the existing force, and our equation of motion. So the first thing we want to do before we start a solution is determine, based off of the information that they give us in the problem statement and what they're asking us to solve for, what would be our governing equations. So I come here and I write out a couple of equations that I think I might need based on what they give me and what they're asking for. So I know I'm probably going to need my natural frequency here, my omega sub n. I know my general formula for omega sub n is the square root of k over m. Now, I've decided to go ahead and plug this in right here and leave these kind of as my givens. If I already have this information, I don't want to plug this into a longer equation later. I'd rather plug in a numeric value. So I'm going to calculate my omega sub n. I plug in my k value here of 40,000, my m of 100, and what I have now is my omega sub n is equal to 20 radians per second. Now, I also realize I'm probably going to need my frequency ratio here. So my r is equal to omega over omega sub n, and now that I have my omega sub n from the previous equation right there, I can see that omega given to me is 15 radians per second, so divided by this now omega sub n of 20 radians per second, I get my r value here of 0.75. The next thing I'm going to need to calculate is my u naught, my static displacement. So my u naught is equal to P naught over k, where my P naught is given to me as 500 newtons here, and my k is 40,000 newtons per meter. So therefore my u naught is equal to 0.0125 meters, or if I want it in millimeters for a certain portion of the problem solving, it's 12.5 millimeters. So now they'll get the opportunity to read through the problem statement, see what they've given us and what they're asking us to solve for, and from there, find our key equations and calculate some of the other variables that we'll need to solve the problem. We can now begin our solution. So the first thing we want to solve for is our steady state amplitude. So this comes from equation 4.23 on page 90 of our textbook. So this is our total response equation here. And this is a rather long, involved equation, which is one of the reasons why we did our key equations first, to kind of simplify down some of these terms here so we don't have equations within equations and expand this even more so. And we also realized that there are some simplifications for our specific problem that we can do for this generic general equation for u of t. So u of t is equal to our u naught divided by the square root of 1 minus r squared, quantity squared, plus 2 zeta r squared, times the cosine of omega t minus alpha, all plus e to the zeta omega sub n t times a1 times the cosine of omega dt plus a2 times the sine of omega dt here. So the first thing we can note here is that the starting transient form goes to 0 over time. So our right-hand side of the equation will go to 0 over time. We also note that this side over here of our equation before the plus sign is our steady state response. So what we can do now is we can plug in some of our known values, simplify this down. We end up with, once we simplify this down here, is u is equal to u naught divided by the square root of 1 minus r squared squared plus 2 zeta r squared. We can then start plugging in our known values here. We know our u naught is that we solved for was 0.0125 meters divided by the square root of 1 minus 0.075 squared, quantity squared, plus 2 times 0.1 times our 0.75 quantity squared. Once we plug in our known values to our general equation here. And from there, what we find that u is equal to 0.027 meters, or in millimeters, 27.025 millimeters. From there, the next thing that we want to calculate is our phase angle. So this is what the second thing they asked us to solve for in our problem statement here. So our phase angle is given from equation 4.21b on page 88 of our textbook. So we have the fact that our tangent of alpha of r is equal to 2 zeta r over 1 minus r squared. We can rearrange, solve this for alpha. We find that alpha is equal to the inverse tangent of 2 zeta r over 1 minus r squared. From here, we can now start plugging in our known values to get our alpha. So alpha is equal to the inverse tangent. We plug in here 2 times. Now we have a 0.1 we plug in for zeta. We have 0.75 we plug in for r. All over 1 minus our r of 0.75 quantity squared. Simplify this down a little bit, we end up with alpha is equal to the inverse tangent of 0.15 over 0.4375, or the alpha is equal to the inverse tangent of 0.3426. So alpha, when we do out the math there, is 0.33 radians. Now from here, we need to go back to the total response equation, which is equation 4.23 here, where we have this whole long one again here, u of t with both sides of the equation here. And from there, we've already solved for the left side of the equation, our steady state amplitude, which is what they asked us to solve for in the first part of the problem, was just that left-hand side of the equation. But now we need to plug this u value that we found here back into this equation 4.23 for our total response. And when we get that there, what we have now is u of t is equal to 27.025 in millimeters. Pay attention to what units we're in here. We're going to stick with millimeters or meters. Times the sine of omega t minus alpha plus e to the negative zeta omega at n t times a1 cosine omega dt plus a2 sine omega dt. So this whole thing here, it's even a mouthful to say. So this is why we like to break it into parts when we solve it, not take out 3-4 pages of paper. Do it piecewise. So from there we can plug back in. We know that our omega is 15 radians per second. Our alpha is 0.33 radians that we solve for, and our zeta is given to us as 0.1. So then we can plug in to this equation down here, and what we need to do is solve this equation now, if we look at it, for our omega d. So looking for our omega d, our damped natural frequency, this comes from equation 3.28a on page 63 of our textbook. Omega sub d is equal to our omega sub n times the square root of 1 minus zeta squared. We can plug in our known values to this relationship here. So omega d is equal to our value for omega n, which is 20 radians per second, times the square root of 1 minus our zeta, which is 0.1 squared. Do that there, reduces down, omega d is equal to 20 times the square root of 1 minus 0.1 squared, or when we solve this out, our omega d has a numeric value of 19.9 radians per second. So now this value here gets plugged back into the total response equation there. So this long equation, again, we're solving this piecewise. So this becomes u of t is equal to our 27.02 times the sine of 15t minus 0.33 plus e to the negative 2t, a1 cosine of 19.9t plus a2 times the sine of 19.9t. So next, we need to use our initial conditions in order to solve for our a1 and our a2 out of this equation. So we've done a lot of work based upon that total response equation, and it is very long and involved, but we're breaking it down piecewise, doing one part at a time so it's not overwhelming and we don't lose anything in our plugging and solving for this. So from our initial conditions, we recall that our initial conditions are given to us in the problem statement here. So U naught is equal to 6 centimeters or 60 millimeters, depending on which units we're working in here. And V naught is equal to 0. Plug these into our total response equation. So we go back to this one here. So U of 0 for initial conditions at time is equal to 0 is equal to now our 27.02 times the sine of 15 times 0. So this whole term goes to 0 here, minus 0.33. This term goes to 0 when we plug in a 0 there, times a1 times the cosine. This goes to 0 there, plus a2 times the sine of this goes to 0 there. This reduces down now. Plug in our initial conditions here for U naught. 60 millimeters, we'll stick with millimeters for everything, is equal to 27.025 millimeters times the sine now of negative 0.33 plus 1 times our a1 times the cosine of 0, which goes to 1, plus a2 times the sine of 0, which goes to 0, so that whole term there goes to 0. So this reduces down even further. 60 millimeters is equal to 27.025 millimeters times the sine of negative 0.33 plus a1 right there. So now we can solve this for our A1. Now, one thing you can note here is I've kind of waited till the end before I really solve things out within this problem statement, just in case more things cancel out. So then at the end, it's a pretty straightforward problem. Going from that very long involved with many unknowns total response equation, we've narrowed it down to this equation here, and now we can solve this for our A1, and we do that. We can rearrange slightly here, so 60 millimeters minus A1 is equal to negative 8.76, or A1 is equal to 68.75. So now, for these same initial conditions here, I can take the derivative of my total response equation there, so u dot of t is now equal to 15 times 27.025 times the cosine of negative 0.33, plus we have all this over here, and we can reduce this down and simplify it even further than it is already, and we can see that on the right-hand side of the equation over here, we have e to the negative 2t, 19.9 a1 times the sine of 0 plus 19.9 a2 times the cosine of 0, and the cosine of 0 becomes 1 there. This goes away because the sine of 0 is 0. So we end up with a reduced equation of 0 is equal to 383, which comes from up there by combining all that, 0.5 minus 2a1 plus 19.9 a2. Well, now we have a value for a1 that we've just solved for on the previous side. We can plug in there. So we get 383.5 minus 2 times our value for A1 of 68.75 there, plus our 19.9 A2. Our only unknown in this relationship now is our A2, so we can solve for A2. A2 is negative 12.36. So all that just to get our A1 and A2, so then we can plug our A1 and A2 back in to our total response equation to get our final solution. So that's what we do there. U of t, once we plug our A1 and A2 back in, is equal to 27.025 times the sine of 15t minus 0.33 plus e to the negative 2t times now our 68.74 times the cosine of 19.9t plus 12.37 times the sine of 19.9t for our final answer. So quite a bit of work to fill in everything we needed into that total response equation, but we were able to do it piecewise, bit by bit, and then slowly plug back in.